NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everybody. I'm Brian White from JPL's Office of Communications and Education. Welcome to the Von Karman series. Now, before we get started, I want to talk about a teacher I had in college who, on the very first, great teacher, on the very first day of class, he drew this itty-bitty tiny little circle on the board. And he said, "This is everything you know." Exactly, that's what we thought as college students. We thought we knew everything. We thought we knew more than a tiny little circle. He says, "It's fine because everything that circle is touching is everything you now know you don't know." Said by the end of the class, he drew this much bigger circle all the way around it. And he said, "I hope this is you, and I hope it's a lot scarier. Because everything that circle is touching is everything you now know you don't know." Ocean worlds are a rich and vibrant part of our solar system that intrigue both scientists and the public alike. Obviously, you're all here tonight. But what exactly are we looking for? And how will we know we found it, whatever it is? Tonight, we'll take a look at some things that we know we don't know and how we go about figuring out which questions to ask. Now, this evening's speaker, Dr. Morgan Cable, is a research scientist here at JPL. While earning her PhD in chemistry at Caltech, she designed receptor sites for the detection of bacterial spores, the toughest form of life. She and colleagues were the first to discover a co-crystal, the equivalent of hydrated mineral, made exclusively of organics that may exist on Titan's surface. This work has led to the inception of a new field, Titan petrology, and she can correct me if I screw that one up. She conducts field work in extreme environments on Earth, searching for life in places such as the Atacama Desert, the summit of Mount Kilimanjaro, and the lava fields of Iceland. She is an extreme unicyclist. She's a surfer who worked on the Cassini mission as a project science systems engineer, is currently a co-investigator on the Dragonfly mission to Titan, and a member of the project science team for the Europa lander. Ladies and gentlemen, Dr. Morgan Cable.
Thank you. Can you all hear me all right? All right. Thanks so much for coming, for braving the coronavirus. Make sure you're all washing your hands. We've been doing the chemistry high five, which is with the elbow. I've also seen some with the foot, instead of shaking hands. It's such a pleasure to be here tonight. I'm so excited to tell you a bit about the work that we're doing here at JPL and other NASA centers to explore this ultimate question, are we alone? So before we get started, I'd like you all to do a little exercise. Now, it's kind of late here, 7 p.m. For those of you watching online, it might be a little bit later, but I'd like you to take a minute to take a breath and close your eyes. And I want you to picture yourself in your mind's eye standing on an alien world. All right, picture it. Look up into the sky. How many suns are there? Is there a single star like we have here? Or is it more like Tatooine? Binary star systems are actually pretty common. Maybe it's nighttime. Do you see different constellations in the sky? Look down. What are you standing on? Is it rock? Is it ice? Sand? Maybe you're floating. Maybe it's a boat and you're on liquid. Is that liquid water? Or is it something else? Picture yourself there on your alien world. Is there a lot of gravity? Is it larger than Earth, and so it's pulling you down, or are you kind of floating? Would you skip around like the astronauts did on the moon? Think about this place. And now I'm going to give you a mission. Your mission, if you choose to accept it, is to collect one sample. Well, not even one. Anything that your arms can carry to prove that there is life on your alien world. Think about what you might grab. Okay? And now I'd like you to open your eyes. This is our only example of a place that has life, right? Our home planet, our pale blue dot, the Earth. And you may think that in a world teeming with life, doing that exercise that I just asked of you would be easy, right? This would be super simple. But is it? Well, it depends on where you land. If you land here, super easy. This is the Amazon rainforest, right? You could just go grab a leaf, maybe a monkey if you're quick enough, you could get something really easy and obvious that there's life there. Okay, that's great. But if I were an engineer trying to design a spacecraft to land here, do you see a safe place to land? Not so much. Chances are I would want to land in a nice flat place. This is the Atacama Desert in northern Chile. It's one of the driest deserts in the world. And we actually love this here at NASA because this makes an excellent analog for Mars. A lot of the salts, the water activity, other things about this environment make it a good analog for Mars. But if you were to try to look for life here, there is life here, but it's not quite as easy to find. You might need a microscope, for example. You might need a tool to dig down underneath the surface a little bit to find that life. Now, what if you went to a place like here? Does anyone recognize the skyline? Yeah, this is Los Angeles. Now, this gets into a different kind of biosignature, something that we call a technosignature. And we're going to save that discussion for another time. That would be amazing. And if we find something like this somewhere, checking that life box would be pretty easy. But chances are, if we were to land anywhere here on Earth, we would land here, right? About 70% of Earth's surface is covered in water. And if you were to design a container to collect life, to bring back, you would design it differently if you were going to land someplace like an ocean than you would if you were landing in a desert or in a rainforest. And so depending on where you go and what you're looking for may define the type of things that you would bring with you to your alien world. And it's appropriate that we end on water because for NASA, this is one of the key ingredients that we look for when we're searching for life. It's not the only thing. Of course, there could be life that is not aqueous-based, that's not based on liquid water. But this is our sample size, right? Sample size of one world. And here, we find that life needs 3 key ingredients. One of them is liquid water. Liquid helps you transport nutrients in, transport waste out. It sort of greases the molecular machinery of life. It lubricates it. So we know that life needs water. We also know that it needs what I call chemistry, basically building blocks. You need something to make those molecules that you are made up of. You need something to make those out of. And that can be carbon, hydrogen, nitrogen, like we have here abundantly. Typically, it'll be something that's pretty common. If we were all based on, I don't know, titanium or iridium, there's not a lot of that around. So there wouldn't be very many of us, which I guess means we wouldn't have as many coronavirus distributor, which would be good. But you typically use building blocks that are common. So that's the second thing. We need the building blocks of life. And the third thing we need is energy, something to metabolize, something to drive the chemical reactions, the biochemical reactions that keep us alive. And so any place on Earth where we find those 3 things, we find life every time. And so these are the things that we will look for when we try to explore our solar system and beyond and search for life there. So let's go a little bit further out from Earth. We're going to go about 480 million miles to Jupiter. Jupiter is our largest planet in our solar system, right? It's kind of the bouncer. It sort of kept a lot of major meteoritic events from happening here on Earth, at least not too many. So we're 65 million years and counting since the last one. That's great. Jupiter is amazing. It's beautiful, and I love it. But I love its moons even more. Jupiter has 4 what we call Galilean moons, because Galileo discovered them, should get some credit. And 3 of them are locked in what's called a tidal resonance. And this one, Europa, is in the middle. So in between Europa and Jupiter is a world called Io. It's the most volcanically active body in the solar system. It's a really cool place. And it's really hot because of its interaction with Europa and also with the 3rd moon out, which is called Ganymede. So it goes Io, Europa, Ganymede. And for every 1 orbit Europa does, Io does 2. For every orbit that Ganymede does, Europa does 2. And so what happens is it's kind of like, do you remember on the playground when you were a kid, if you pushed your friend or maybe your sister or brother on the swing set and you wanted them to go really high, you had to time the pushes just right. And if you did that, you could get them go maybe higher than your parents thought was safe. That's what's happening here with these worlds. So they're locked in this gravitational tug of war, and because of this resonance, every time they orbit around, they give each other this energetic kick. And here, that kick turns into this friction that causes the worlds to move like this. And so that flexing, we call tidal flexing, that generates heat. And that's why Europa has a lot of liquid underneath this icy shell. And it's why it's one of my favorite places in the entire solar system. Europa actually has 2 to 3 times the volume of all of Earth's oceans combined in liquid water. That's a lot of water. Now, it's under a shell of ice. But it's really interesting because you can learn a lot about this world, we think, from studying Europa's surface. Now, you may notice that it's got some cracks and some grooves, and they seem to be a darker color. We're not sure exactly what that dark color is. We think it could either be salts or organic molecules, maybe a little bit of both. But one thing is kind of missing from this. Does anyone know? I'll give you a hint. Our moon has a lot of these. Yes, craters. Turns out Europa only has this many. It's got about 7 big craters. Now that's important because this is how we date objects in our solar system, by crater counting. And this tells us that the surface of Europa is relatively young. Now this is cool. It's about 50 million years, so even younger than the dinosaurs, which means something must be refreshing it somehow. We think that there could be some activity from the ocean, maybe some localized heating. We see these things called lenticulae, which is Greek or Latin for freckles, some places where it looks like there are little hot spots. We see these smooth bands where it looks like some of the surface has split open and water has been sucked up or ice has been sucked up and filled in the gaps. And so we see these places on the surface where it looks like there's a lot of activity. And that gets us really excited because we would want, if we send something to explore this place, to search those fresher regions. Those may have more organics in them. They may have better evidence of what's in that ocean underneath. And boy, wouldn't it be great to send a spacecraft here and look for life or look for evidence of habitability? Yes, it would, and we're going to do that. Europa is incredible, right? We think that underneath this ice shell, we know that it has a liquid water ocean. We're not sure exactly how deep it is. That's one of the things that our next mission is going to study. But we do know that there's a lot of radiation at the surface. This is because Jupiter is really big. It acts as the bouncer for the rest of our solar system, which is great, but it also has some negative effects for some of the moons around it. Because it's so large, it sucks in a lot of the charged particles from the solar wind, and it whips them around with its really strong magnetic field, and it slams them into Europa. Now, Europa doesn't have an atmosphere, and so these things will interact directly with that water ice on the surface. And water ice is H2O, right? That's water. It'll break that up, it'll kick off the hydrogens, and since they're super light, they float away, and so you'll end up with this tenuous oxygen. We don't even call it an atmosphere. We call it an exosphere because it's so thin. And that oxygen is really rich in electrons. Now, down at the sea floor, where we think there could be hydrothermal activity, heating, geothermal activity, things like that, we're pretty sure, based on examples here on Earth, that place is electron poor. So if you've got a lot of electrons in one place, a few electrons in another place, you know what that is? That's a battery, basically, right? You just need to connect the two. And there are a lot of types of life here on Earth that we call chemotrophs, chemoautotrophs. Chemo means chemistry, auto means it does it by itself, it doesn't need help. And it uses those types of energy sources, just shuttling the electrons around, takes a little tax, a little bit off the top, and that's what it uses to be alive. And so there are all sorts of organisms that could exist in environments like this. And the Europa Clipper mission is going to study this world. So Europa Clipper is a mission that NASA is building right now. It's going to have 9 different instruments that will be able to study Europa, its surface, its interior, and all of these properties to help us understand whether or not it's habitable and whether or not there could be life there today or maybe in the past. Europa Clipper is going to be ready for launch in about 2025. As I said, we're building it now. And depending on which rocket we go on, we'll reach the Jupiter system maybe 6-ish years later. And we'll bring all of these instruments to bear. We're going to have some very sensitive cameras that will be able to take incredibly high resolution images of Europa's surface. We'll have basically a fancy compass, magnetometer, that can tell us, by studying the magnetic field, properties of that ocean and its depth. We'll have a radar sounder that can do the same thing we do here when we fly radar over Antarctica to get at the thickness of the ice and if there are any pockets of water in there. We'll also have an instrument called a mass spectrometer. And we actually have two different kinds. One that can get at the gas. It's sort of like your nose. It'll sniff what's there, things that are coming off the surface, to tell us if there are any interesting gases like hydrogen or methane, things that we could tie to some sort of geothermal activity. And we'll also have one that it's kind of like sticking out your tongue and tasting snowflakes, except doing it at 5 kilometers a second. Would not recommend doing that with your tongue, but with the instrument aboard, it's a dust detector. That is actually the perfect speed to pick up dust grains, ice grains. You smash them open and you can determine what kind of organic molecules are present. And we can do that for bits of ice that are sputtered off the surface from micrometeoroid impacts and things like that, and get an idea of what that surface composition is, even without landing. So the Europa Clipper mission is going to be in the Jupiter system for several years, but we decided to not have it orbit Europa because of the intense radiation. It's not so good for us. If we were standing on the surface of Europa, you'd probably get a lethal dose of radiation in a few hours. It's not good for spacecraft either. It can cause things like single event upsets in your electronics and make them function, turn on and off in ways that you don't expect. And so what Europa Clipper is going to do is it's going to get close to Europa, take lots of data, and then come back out, cool off, send the data back, give us some time to interpret it, think about it, before it goes back in again for its next pass. This is something that we're really excited about because we'll be able to get images that every time we send a powerful spacecraft somewhere and we bring advanced instruments like cameras, detectors, the electronic tongue I was talking about, we always find things that surprise us. And I can't imagine the things that we will find here that will surprise us. Now, when NASA does missions, typically we like to send an orbiter or a flyby mission first. Now, there's some reasons for that. This can give us a lot of great images and maps of the surface. One of the other instruments aboard Clipper is basically like a really fancy camera for every picture that it takes. Each pixel of that image will actually be a spectrum, and that will give us information about what the surface is made of. Those kinds of details are really important because ultimately, if we want to answer the life question, we need to land. And we are working right now on a concept. This is called the Europa Lander. This is something that would come after Clipper and be able to take all of that information to help us pick just the right spot to land, right? We want to go to a safe place, but an interesting place that could potentially have signatures of life. It will have the ability to communicate directly with Earth through its high-gain antenna, and it will have an arm, that would be able to cut into the surface. Now, the surface of Europa is pretty cold. It's about 150 Kelvin, which, let's see, in Celsius, that's what, minus 130 degrees C? I don't know what it is in Fahrenheit. I'm a scientist. We don't work in Fahrenheit, but it's really cold. And it turns out that ice at those temperatures has a lot of similar properties to rock, like granite. And some of our engineers here at JPL who are designing types of cutting tools to be able to slice into that really hard ice, boy, they're really interesting. One of the guys was telling me, yeah, I was on my treadmill this morning. I was thinking about what is the toughest sample that we could come up with. And he ended up, oh, this is really mean. He took cotton and he stretched out the cotton balls until you get like that really fibrous kind of stuff. And then he put that in water ice and then dunked that in liquid nitrogen. And he said that broke about half of their prototypes because the fibers, tripped up all the blades. But the reason that we do that is because we want to be sure that we have over-engineered everything such that even if the surface is something we wouldn't necessarily expect, we can still do our science. That even if we land in a place where there are bigger rocks than we expected, there might be some weird fibrous things, we could still cut some of that sample, hopefully not destroy some really sensitive organism, and bring it in and look at it with our instruments. And so that's what this type of mission concept would be able to do. So Europa is a fascinating place, but it's not the only place. there are a few other worlds I'd like to tell you about tonight. So let's go a little bit further, actually a lot further, out further away from the sun. So you know how you've got those like nice diagrams of the solar system, and it shows like the sun and then Mercury and Venus, and they're all kind of evenly spaced out? You know they're not actually like that, right? Like the distance from the sun to Jupiter, you've got to do that again to get to Saturn. Space is big. Okay, so if you're here at Saturn now, the sun it's not 10 times dimmer. The distance is 10 times, but the light intensity varies. Do you guys remember this from high school? 1 over r squared, 100 times dimmer, right? Because it's 10 squared. So things are very different around Saturn. We were fortunate to have a spacecraft in the Saturn system called Cassini, which if you're here in the room, is right over there, a scale model. Cassini launched in, 97. It arrived in the Saturn system in 2004. Space is big, and was there for about 13 years. And I was lucky enough to be involved in the Cassini mission right near the end of its time in the Saturn system. We learned so much about Saturn, its rings, and its moons. And one of the ones that surprised us the most was this one. This is one of my favorite places. This is Enceladus. Small things can be mighty, I know. Enceladus is relatively small. It's about the size of Arizona, but really amazing things are packed in this tiny package. It is the whitest and brightest body in the solar system, which tells us that the surface is mostly just really reflective snow, water ice. And you see that cool thing spewing out of the South Pole? Yes, that is a plume, and that surprised all of us. When we built Cassini, we didn't think there was liquid water out this far. So we cleaned it, but we didn't sterilize it. That's actually why Cassini ended up doing its swan dive into Saturn when we reached the end of the spacecraft's life, because we didn't want to contaminate places like this. Enceladus, in its south pole, it has these 4 big cracks. They're called tiger stripes, because it looks like a giant tiger just went like that. But these are really big. They have to be a very large tiger. They're about, 3 marathons long. The marathon's what, 42 kilometers? 42, answer to everything? Yes. And they're a little bit less than a marathon in between each of them. So these are really large cracks. And coming out from them is a lot of water. It starts out as liquid. This has a liquid water ocean, just like Europa. And when that water comes out into space, it freezes. And then it can reflect light beautifully from the sun, which is what some of these gorgeous backlit or frontlit images are. And it's spewing out tons of just free sample from its ocean into space. No need to dig or drill. It's just like NASA. You want to find life somewhere? Come on down. Get your free sample right here. Now, when we built Cassini, we didn't think there was liquid water out this far. We sure didn't think that there could be life this far out. And so Cassini did not have life detection instruments on board. But it was still able to fly through this plume multiple times and use its instruments to give us some hints of what we think is there. Just like Europa Clipper, Cassini also had that tongue that could stick out and collect some ice grains and figure out if there are organic molecules there, and it found some. It had a sniffing instrument, so it could sniff gases, and it found hydrogen and methane, 2 things that we know organisms either eat or poop out. Either way, it's exciting that they're there. And it also found evidence of hydrothermal vents, like we think are also present on Europa. We found 3 separate lines of evidence that tell us there could be places at the seafloor where water from the ocean goes underneath, gets heated up, and then comes back out. Now, this is a video of a hydrothermal vent here on Earth. I would love if this was taken at Enceladus. We're not quite there yet, but we're working on it. These places are very rich ecosystems of life, not just bacteria, but crabs, octopus, octopods, I think is the plural officially of octopus. We see tube worms, all sorts of advanced organisms, and they're living as far removed from sunlight as you can get here on Earth. Now this is important, right? Because all of these ocean worlds I'm showing you have a thick layer of ice that's shielding that ocean from sunlight. Almost all life here on Earth needs sunlight, directly or indirectly. If you are a plant, it's direct. If you eat a plant, it's indirect. And so we seek evidence in communities like this, these rare places where sunlight doesn't seem to be needed, to give us clues to what we might look for in these worlds. And so a lot of NASA scientists will study these hydrothermal systems here on Earth, or ask our oceanographer buddies to give us some hints and some clues as to what we might look for and where we might get tripped up if we're trying to design an experiment to look for life. So Enceladus is another fascinating place, but I want to tell you about one more. This is one of the bigger moons in our solar system. It looks tiny next to Saturn. You see that little sort of golden dot? That's Titan. Titan is the second largest moon in our solar system. If you count its atmosphere, it's actually the biggest. But we'll give Ganymede a win because otherwise it's not quite as fascinating. Titan has an atmosphere that's actually thicker than Earth's. And thanks to a collaboration between NASA and the European Space Agency, the ESA, we were able to land the Huygens probe on the surface of Titan. And this is the image that it took. Now, it kind of looks like Earth, right? You see some dirt there. It's probably a really hazy day here in LA, right? It's kind of yellowish brown. And you see some pebbles there, some rocks. Those are not rocks as we know it. Those we think are made out of water ice. And that brown stuff, we think is a mixture of complex organic molecules that are made in the atmosphere. Actually similar to smog. We think it's photochemistry. It's the same way smog is made. So light interacts with some gases. Those gases start to link their atoms together to make bigger molecules, and those reactions continue to happen, and you get bigger and bigger aerosols that eventually get big enough that they rain down or snow down on the surface. We think that's what's happening. But there's still a lot of unanswered questions about Titan. One of the coolest things about Titan is that it's not just rocks, it's not just, it has clouds, it has an atmosphere, but it also has liquid on its surface. Titan is even colder than Europa though. It's minus 183 degrees C, which is 90 Kelvin, and I don't know what that is in Fahrenheit, but it's even colder. However, if you were standing on the surface of Titan, you would not actually need a spacesuit because of that atmosphere. You'd need a heck of a parka, like a really thick one. Frostbite would be a thing. But you could walk around without that pressurized spacesuit. The pressure is about 1.5 times our pressure here on Earth at sea level. And so because of that, a lot of really cool things are possible. We also see rain happening on Titan, but because it's so cold, it's not liquid water. Water is frozen solid. We see lakes that are made out of liquid hydrocarbons, methane and ethane. When I give talks to kids, I say liquid farts, and they all get really excited. Sometimes adults do, too. I love it. It's great. But this is fascinating, right? Because if you remember from maybe middle or high school chemistry, water is a polar solvent, right? Methane and ethane are the opposite. They're nonpolar. And you may recall like dissolves like. Anything that dissolves in liquid water is not going to in these liquid hydrocarbons, and vice versa. And so we have these huge seas. They're as big as the Great Lakes and bigger, that are filled with this liquid that couldn't be it could not grease the machinery of life as we know it. But it could potentially do that for some other weird alien chemistry that would have to be, by definition, very different from any biochemistry here on Earth, just to be able to stay dissolved and work in a liquid like this. So just in our own cosmic backyard, we have this wild example of something that, boy, it would be really nice if we could go here and study this world more. So it's got this cool stuff on its surface. But people always forget this. Titan also has a liquid water ocean underneath all of the cool stuff happening on the surface. You've got those liquid hydrocarbon lakes, that cool organic-y stuff that we don't know what it is, and then you go down through the ice, which is the shell, and you hit liquid water also. Now this is really exciting to me for someone who is a chemist by training. I study organic chemistry because we have tried to replicate some places in Titan's environment here in the laboratory. We can do that same photochemistry that makes that gunk in the atmosphere. Carl Sagan was actually one of the first people to do this in the lab, and he named that stuff. He called it tholin, which is from the Greek word tholos, which means muddy or not clear, which is really great. It's a double meaning because the stuff, when you make it, it's like that brownish, orangish color, so it's sort of mud colored, and we also don't know what it's made of. Because you stick it into an instrument and you get this forest of peaks. It's like anything that you can think of that's made out of carbon, hydrogen, and nitrogen. Those three elements, you mix them together whatever way. Do you have your chemistry set at home? Anybody? I do. No, you don't do that for fun? But you can make small things, big things, it's all in there, in this tholin. And the really cool thing is, if you take that tholin and you dissolve it in liquid water, you make amino acids like that. So if any of that organic-y, goopy stuff that's made in the atmosphere, that's stuck on the surface, if any of that gets pulled down into that liquid water ocean, boy, you've got a lot of interesting molecules now that life could use, potentially. And so this is why I think Titan is a really fascinating world, worthy of study. Boy, wouldn't it be great if we were working on a mission to go there? We are! This is Dragonfly. This is a brand new mission. It was just selected in July of last year, and it is big. This is an 8-bladed rotorcraft that can move. Remember I said the atmosphere is thick? The gravity in Titan is a lot less. It turns out it's more efficient to fly around than it would be to drive, like our typical rovers do on Mars. And this thing is large. Like our first science team meeting, they had the VR headset so we could see how big it is. And like, okay, I'm not normal size human, so picture a little bit bigger than me, but it's like, I put out my arms and I can't quite reach as wide. Like it's big. That antenna, the direct to earth antenna, that thing that folds up and back is like taller than me. I was looking up at it. This thing is big. But because of all the advancements in rotorcraft technology, in autonomous navigation, this type of thing is possible to do now, which is super exciting. Because this means we can land in one spot, study that place, and then pick up and go somewhere else interesting. So we can study these dunes that we see in the equatorial region of Titan. That's where we're going to start. We're going to start near a crater. Titan also doesn't have very many craters, but it's got a few. And it's a great place because it looks like that impact excavated some stuff out, and some of the water ice may be really accessible. And so we're going to go there too, and we're going to just hop around for a few years. This is going to launch, we hope, in 2026, land on Titan in 2034. Space is big. And don't count how old you will be because you might get depressed, but I'm really excited about this mission. So the future is really bright when it comes to the types of missions that we're working on, that we're building to answer some of these critical questions about ocean worlds and whether or not we're alone. But this is just in our own cosmic backyard. What about further than that? I'd like to introduce you to the TRAPPIST system. So this is about 12 parsecs out in the Aquarius constellation. So if you're a really good pilot like Han Solo, this is one Kessel run away. I'm glad you went with me on that one. It's got about 7 planets in orbit around a red dwarf star. Now this is a place that we are just starting to study, but there are a handful of worlds even in this system that are in what we call the habitable zone. Now what is that? Well, that's where Earth is. If you're too close to your host star, things get a little bit hot and liquid water is not stable at the surface. It would all boil away. If you're too far, you end up with the opposite problem, right? Things get frozen solid. Earth is in just that right happy place where liquid water can be stable on the surface. And when we look at exoplanets, that's what we call these, planets in orbit around other stars, we start off looking in that habitable zone because those worlds may be similar to Earth. And we've started a catalog, and just in a few years of looking, we've already found a bunch. You can see some that say TRAPPIST-1, whatever, there's a letter at the end. That's typically how we name exoplanets. We start with the telescope that found them, so the TRAPPIST, or the mission that found them, is first. Then we give it a number for the star that we observed, and then the planets all get letters, so A, B, C, D, E, so you can figure out where it is, how close it is to its host star. And so you can see TRAPPIST, D, E, and F, and G all seem to be in that habitable zone. And that's just around one star. And we've just started looking. This thing is probably already out of date. It's from September of last year, but I'm sure we found a few more. And this just blows your mind, right? These are just the ones in the habitable system. We haven't even started looking for exo-Europas and exo-Titans and exo-Enceladi. So, and now we know that liquid water can exist even further out than this habitable zone that Earth resides in. It's an incredibly exciting time to be a planetary scientist and be studying these worlds. But looking for life on a place this far away is challenging, right? If we wanted to send a spacecraft there, it would take a very long time. We're working on concepts like that. There are some spacecraft that we're working on using things like solar electric propulsion or even lasers to accelerate them to a significant percentage of the speed of light. which is nuts, because then how do you slow down? But we're working on that too. And to get to these worlds so that we can study them, we can still do a lot with powerful telescopes here on Earth. One of the nice things we can do is if some of these worlds are just the right angle where they pass between us and their host star, we can do spectroscopy. Spectro is light, and scopy is study, so we're studying light, spectroscopy. So we can break that down into the rainbow and look at what wavelengths are missing. And by doing that, we can tell what kind of gases are in the atmospheres of some of these worlds, which is pretty amazing. But the search for life can have challenges, right? It can be tough. Who recognizes this image? Yeah, this is, does anyone know the name of the meteorite? Very good. It's ALH 84001, which, do you want to know how meteorites are named? I'm going to tell you. Guess what? All right, so this was a Mars meteorite that was discovered in Allen Hills, Antarctica. That's where the ALH comes for. The 84 is from 1984, because that was the year that it was discovered. And then the 001 it was the first meteorite that was found that year in this place. They leave a couple extra digits because I guess they're hoping they'll find, maybe 100 or more. That would be great. We haven't found that many Mars meteorites though. We found about 30 so far. And most of them we do find in Antarctica because it's nice and white. There's not a lot of snow or anything else happening. And so these black meteorites show up brilliantly. They're very easy to find. So this one, ALH 84001, is the oldest Mars meteorite that we've found. We think that it's from a time in Mars's history when it was much warmer and wetter. Now the reason we know it's from Mars is because there were some trapped gases inside that we were able to sample, and those gases are the same as in Mars's atmosphere. We also have some other evidence to show us, to prove to ourselves as scientists that this is from Mars. And when we sliced it open and looked at it under a scanning electron microscope, this is what we saw. And of course, we all immediately got very excited, right? Because that thing looks like a worm. Well, it's not. It's about 1/100th the width of a human hair, which is incredibly small. Very few cells are even that small, much less a multicellular organism like this. But it gives us some lessons as to when life can, or when evidence that we think as biased humans that we see looks like life, whether or not it is actually life or not. So we studied the chemical signatures that were in this meteorite. And there is still, to this day, some scientists, a small subset of the community, that are convinced that this is actually evidence of life. But the problem is it's hard to convince the rest of us. And the reason for that is because there are abiotic explanations for all of the things that we see here. We see some carbonate globules. Carbonate typically is associated with life, especially fossilized life, but you can also make it without life too. We see magnetite crystals inside of this meteorite. Now, some bacteria will actually use magnetite, kind of like little compasses, to sort of navigate around. But the amount of magnetite that we saw was inconsistent with what we would expect for most organisms. The amount that we saw would have meant that Mars's magnetic field would be super strong, like way stronger than Earth's, and that doesn't make sense because it's smaller. How could it? That doesn't make sense. And you can also deposit that abiotically too. So Carl Sagan said once that life has to be the hypothesis of last resort. You must have eliminated all other possible explanations. And if you can do that, and the only thing you're left with is life, then you can be convinced. And the problem with this meteorite is there are still enough abiotic explanations for this that all of us can't be convinced. And this is something that we have here on Earth. So we can bring to bear all of our most sensitive instruments, some of the microscopes and spectrometers that fill a room, right? What if you want to take that and now put it on a spacecraft, miniaturize it, and then send it somewhere else? Some of the instrumentation, it gets challenging, right? You may not be able to be as sensitive, but now you can be sure that you know exactly what happened to your sample in between when it was there on Mars, for example, like with Viking, and when you reached out your robotic arm and grabbed it and then looked at what was inside. With meteorites, we can guess at when they formed. That meteorite that I was showing you, it probably was ejected from Mars millions, maybe billions of years ago when it was warmer and wetter, and then it just kind of circled around in space for a while, we think until about 16,000 years ago, and that's when it crashed here on Earth. We don't really know what was happening to it during that time, And that uncertainty can lead us to question anything we might find inside it. That's why we want to go and land on these places where we have a better understanding of what we call the provenance of that sample, the history, where it's been, how it got there, so that if we find a signature in it, we can say for sure that came from this place, it's not contamination, it's not something it picked up later. That's really important for being sure when we finally answer this key question, are we alone? We can be sure of our answer. So the Viking landers, there were 2 of them in the 1970s. These landed on the surface of Mars, and this was the first mission that explicitly had the goal of looking for life somewhere else, on Mars in this case. The Viking landers, they had identical instruments, and they went to 2 different places on Mars's surface, and they had 3 biology detection instruments. They also had a chemical analyzer called a mass spectrometer. Remember the tongue? It's like similar to that. Of those 3 biology experiments, 1 gave a positive result for life, 1 was negative, and 1 was ambiguous. Now, this isn't because the scientists did a poor job. They did the best job that they could, designing an experiment that they thought would give them that absolute yes or no answer. But all 3 of these techniques were based off of metabolic assays. Basically, what they did is they scooped up some Mars soil, some Mars regolith, they put it in a bin, and then they dropped either water, liquid water, or some nutrients on it, or both, and sealed it up, and they looked at the gases that came off, or they looked at whether or not it could take some of the nutrients that it was given, and be able to turn that into other molecules that could give us evidence of life. So these tests were based off of them going to different places here on Earth and trying those same experiments. And they thought that they were very confident that these types of things could give us an absolute yes or no answer. Are we alone? Well, it turns out that we didn't have as deep of a knowledge of the surface chemistry of Mars at that time. Since then, we've discovered that there are things like perchlorates, very reactive salts, that can give the same types of answers. It turns out a scientist recently was able to replicate very well, not perfectly, but really closely, those same false positives, what we call it, when you see something that you think is real, but it's not. Those false positive measurements, if you take perchlorate and you sort of give it a light dusting of gamma rays, and then you do that same sort of life detection measurement, you dump some water and some nutrients on it, you'd get the same gases off. And so, as Carl said, life has to be that hypothesis of last resort. And in the case of the Viking experiments, we still have abiotic explanations that could explain the data that we see. But we've learned a lot since then. When we were building and launching the Viking landers, we didn't know about the 3rd branch of life. We knew about bacteria and fungi, but we didn't know about archaea. That hadn't been discovered yet. We know a lot more now than we did then. It doesn't mean, though, that we won't make new mistakes whenever we search for life elsewhere. And that's something that, as scientists, we always need to keep in mind. We will do our best to design the most foolproof experiments, but we have to prepare ourselves for the fact that we will likely make new and different mistakes. We'll still learn something, and we still have to go, because we need to know. But we need to make sure that we're prepared for an answer. And so that's something that I always try to keep in mind when we're having these endless discussions about what experiments we should do, how sure we can be, how many tests we can do here to be positive that we're spending our taxpayer dollars, your dollars, as well as we can, right? Because that's what NASA does. And we can take a lot of lessons from the types of life that we have here on Earth. Does anyone recognize this little guy? The tardigrade, the water bear. This little guy can survive in space, right? I think he's super cute. One of my friends said, boy, it would be terrifying if that was like large enough to ride. I think that'd be amazing. Could you imagine like riding around? It'd be awesome. So we have examples of life that can survive really extreme conditions. How would you look for a tardigrade? Would a microscope be enough? That would just be a morphology type of measurement. What if you saw it move? That would be better. Maybe if you also were able to study some of the molecules that the tardigrade is consuming or producing, or maybe, sad to say, maybe just take the tardigrade itself and stick it into an instrument and see what it's made of. These are types of things that we could do if we expect this kind of life. But we see some other weird things too. This kind of organism, I can't remember its name, but it doesn't need oxygen. It's one of the few animals, even though it's microscopic, it's an animal that doesn't need oxygen to be alive. This is a brand new sea slug that's new to science, discovered just last year. So we're still finding, even on our own planet, all sorts of wacky and wild forms of what look like alien life. And this guy, this is something we call the immortal jellyfish. It's about the size of your pinky nail. And it does this weird thing. When conditions get bad, it reverts back to its sort of primordial polyp form, and it just kind of chills out. And then when conditions get good again, it makes itself back into a jellyfish. So we think this thing could potentially live for a really long time, maybe forever. Forever's a long time, but at least for a very long time. So we try to take lessons from the extreme forms of life that we see here to help inform those tests that we might perform somewhere else to answer that pivotal question. Because this is what we're going for, right? At least, you know, it'd be great to write my speech to go and collect the Nobel Prize for finding life for the first time in human history. This is something we call civilization-level science. You only get to make this discovery once. And it would revolutionize, I think, our opinion of who we are as a species. Whether or not we're alone. Is the Earth just this precious, terribly alone ball, or is it one of millions and billions that are out there that could potentially all have different various forms of life that we couldn't even imagine? We have the technology to answer this question now, and we're building missions to go and find these answers. It's an incredibly exciting time to work for NASA, to be a planetary scientist. And I don't even need that. I would just be so happy to be part of this question of trying to find the answer. But there is that other potential that maybe we search for life here in our own cosmic backyard and elsewhere, and we come up empty. Do you recognize this image? It's the 30-year anniversary, actually, of the pale blue dot, which was taken by Voyager 1 spacecraft. The last von Karman lecture, I believe, focused heavily on this. What if this is all there is? I find that terrifying, but in a way it could also be really gratifying to think that we are this precious, that this world just happened to be the magical place where life can happen. And boy, it really makes you think about how we want to preserve that and keep it going. Maybe go over to Mars and, you know, set up a colony there just in case the next 65 million year meteor, we don't want that to happen. But that would be a revolutionary discovery too. And either way, as a scientist, I want to know. I want to ask the question. I want to design that experiment, or help to design that experiment, where we end up with that single hypothesis of last resort, that the only explanation could be life. It could not be made abiotically. And then I want to go and figure out what that life is. Right now, we only have a sample size of 1. That's it, right? This could be all there is, or it could be one small grain of sand in an immense universe of worlds that could all have life of their own. And I want to be part of finding that answer. So I want you to go back now. Close your eyes again. I know it's like 45 minutes later, but you can do it. I believe in you. I haven't heard any snoring yet. You guys have done so well. And go back to that alien world again. Except this time, it's not you standing there. It's a robotic version of you. It's a robotic exploration spacecraft. So now when you look up at that sun or those suns in the sky, it's not just the light that you see. Now you have a spectrometer, and you can break down that light and figure out what the energy profile is and how that light might be utilized by life that's on your world. Now, whenever you look down, you can figure out what the rock distribution is and which one is most likely to have maybe a microbe hiding underneath it. Now you have instruments inside of you in your belly that when you take a sample and you put it in there, you can be sure that that has the signatures of life for the first time in human history of an alien somewhere else. That's what we do at NASA. That's what I'm helping to work on with my colleagues, is to be able to extend our senses further out into the solar system and beyond. I want to be able to take that circle and expand it out further than I can possibly imagine, to stretch it out as far as I can during my time here as a human. And that's just why I love terribly what I do. Thank you very much.
Folks, we are going to open up for some questions right now. If you are in the house and you've got a question, you're going to line up right behind that microphone over there. We also have some questions from our online audience as well. So while you're all thinking about maybe a question you're going to ask, I'm going to go online here to the great Mosasaur from YouTube asks, although there isn't a concrete answer for this, in your opinion,
My opinion. Okay.
do you think we can find life on these worlds? Can we expect to see it in our lifetime?
I think so. Otherwise, I would be spending my energy doing something else. Again, with just the sample size of one, we have some guesstimates of the types of life we would find. Chances are they're going to be small, microorganisms, just based on the energy that's there. And we have some estimates of how many organisms we might expect in some of these oceans. So we have some idea of the types of life and the amounts of life we might find. And some of the instruments that we are working on miniaturizing and sticking on spacecraft right now have limits of detection that are sensitive enough that they could find those things. That's why I think that we have the ability to answer this question now.
Another one from online, from Space Debris on YouTube. It's kind of similar to what you were just answering and what the last part of what you were talking about. Besides knowing we're not alone, what is the best value for humans in finding life on another world?
For me, it's knowing that there are so many other possibilities out there. I mean, if we're not asking these big questions, the things that when we were much earlier on in our history of just starting to be humans and we looked up from that campfire up into the stars at night and wondered about them, that's what sets us apart, right? Otherwise, we're just what, like eat, sleep, reproduce, and die, and that's it? You know, this is the thing that drives us, that makes us human, is to ask these questions why. And because of that, we want to strive to know the answers. And as soon as we know the answer to that question, we're going to have so many more. It's going to be this amazing, beautiful cycle, and I want to kick off some more of that.
I think we've got a question here in the house.
This is a very, very interesting lecture. I really like it. So you talked about the non-polar versus the polar, and how if those mix, I guess it was on Europa. It was in Titan that would mix. Yeah, mix on Titan. Oh, because there's actually water under Titan, even though. So my question is, so you have all this carbon on Titan. Why do we have any idea why we have a planet, a satellite at Saturn that's heavily carbon, and then we have Io at Jupiter that's heavily sulfur? Why don't we have one of each on both, circling both Jupiter and Saturn?
That's a great question. Well, a lot of these worlds probably do have a lot of carbon and sulfur, but it may be in different forms where it's trapped in the crust or underneath the ice shell. Titan, we're lucky because of its atmosphere. It's outgassing methane from its interior. We're actually not sure why it's still doing that, because if you look at the amount of methane that should be there, it should have run out in, 100 million years. So there's probably some funky cycle that's going on, and we're catching it at a good time. But that methane is what's broken up by light, methane and nitrogen. So you've got CH4 and N2. And you break those apart and you make all sorts of other different CHN things, and that's what the photochemistry is making, that's depositing on the surface. There are other worlds where you still have reservoirs of carbon, maybe as methane ice, like Pluto is very rich in methane ice, for an example. As you step further into the solar system, closer to the sun, you don't have as many volatiles. The things that are gases here freeze out as ice is further out, but you have other complex organic molecules like we have here on Earth. A lot of the organics that are here are probably were deposited by comets and meteoritic impacts over millennia. And so that's another great source of carbon.
Thank you.
All right, and this will be our last question in the house. If you don't get a chance to ask your question, Morgan is going to stick around for a while. She said she will answer everything that comes up here. So good luck to that. But our last question in here.
Yes, what promising technologies do we have at this point for getting through the layers of ice into the oceans of these water worlds.
Okay, I could do a whole other talk just on that. So there are a few different architectures that NASA scientists and a bunch of engineers, both at NASA centers and universities and other companies, are working on. There's one we call it a melt probe. It's something that would have a heated tip. There are a bunch of different ways you can do that would slowly melt away or sublime if you're in a vacuum, right? The solid would just turn into water vapor and go away. You can use that to get down. There are also some robotic techniques. There's a concept that I'm working on with some colleagues here at JPL called EELS, Enceladus Extant Life Surveyor. It also is like snake-like, so EELS, get it? We love acronyms, if you haven't noticed. That could maneuver down through those open tiger stripes in Enceladus and potentially reach the ocean that way. So there are a bunch of different things we're working on, because getting to that ocean would be the ideal place to look for life, because then you could take in your sensor and you could just filter water for as long as you wanted until you got the concentrations high enough to be sure that if there was even one cell in gallons and gallons of water, that you would find it.
And how would we get the information back from the probe?
How would we get the information back? So there are some theories about that. You could have a tether, but if there are some geophysical tidal flexing things that could break the tether, you could deposit pucks that could communicate, that would have their own little power supplies that you could connect. So there are a bunch of different ways that we're looking to try to answer that question, because that kind of engineering is super fun, the really challenging things.
Do we know enough about the cracks on Europa to know if a similar type of eel-like device could get through the cracks there?
That's a good question. There is some preliminary evidence that Europa may have a plume as well. It hasn't been verified yet. We've seen some funky things with the Hubble Space Telescope. We've seen what looks like water vapor in places it shouldn't be. And some scientists went back and looked at the Galileo data. Galileo was a spacecraft that went to the Jupiter system in the 90s and early 2000s. And the magnetometer, that fancy compass, found some weird readings that might be consistent with a plume of water vapor. But my understanding of talking to the geologists and the geophysicists is that a crack, since Europa is bigger and its ice shell is thicker, it might not propagate all the way to the ocean. Instead, if there is a plume, which Europa Clipper would confirm, if there is one, it's probably from a near-surface reservoir. And if that's true, well, could life get up there? If it could, would it still be alive? Chances are it might be very salty. Will that affect things? There are a bunch of things that we would need to think about to understand the provenance, right, the history of that sample.
Great.
Thank you.
That's all the time that we have for tonight. Real quick, join us next month, April 16th and 17th, where we kind of what we're looking at right here, how NASA observed Earth from air and orbit. But before we go, let's give our speaker another great big round of applause. Thank you for joining us this evening. Have a wonderful evening wherever it leads you, folks.